Hi everyone. In this lecture, I will summarize the architectures, patterns, and technologies that you will learn and use in this course. Let's start with microservices powered by Spring Boot. You will learn and implement microservices that communicate through events. A microservice is a fine-grained service, and it exposes endpoints with a lightweight protocol. Microservices has numerous advantages, such as independent development and deployment, easy horizontal scaling, better fault isolation, and enabling use of different technologies per service. Besides these advantages, it also comes with a cost. Since microservices work in a distributed architecture, it will require to use correct patterns and tools for managing the services and for communication and transaction management between these services. In the coming points, we will focus on the architectures and patterns that will help to solve these problems. Clean and hexagonal architectures. These architectures help to develop and test the business logic of a software independent of the infrastructure, such as databases, message queues, or any runtime tool or device. Clean architecture principles will help you develop long-lasting applications that are easily adaptable to any new technology. In this course, while implementing each microservice, you will be applying the clean and hexagonal architectures. The hexagonal architecture, also known as ports and adapters, and is invented by Alistair Cockburn in 2005. It basically relies on defining well-defined interfaces, which are called as ports, and implementing the interfaces with replaceable adapters. There is also an architecture called onion architecture, which has a similar structure with hexagonal architecture, and both has the idea of isolating the domain logic from the outside dependencies. The clean architecture proposed by Robert Martin in 2012 covers a clean architecture in detail, including the concepts of hexagonal architecture and onion architecture, but also adding the detailed definition on the implementation of the domain layer. Clean architecture uses the principle of dependency inversion to strictly follow the dependency rule that only allows an outer ring points to inner ring and never the other way. I will explain the details of these architectures in the coming lectures, and most of the time I will use the terms clean and hexagonal interchangeably. Domain-driven design. In each microservice, when implementing the business logic, you will apply the domain-driven design principles. It basically provides some strategic and tactical patterns that help you to implement your domain logic in a way that's easier to understand, develop, and maintain. You will learn and use entity objects, aggregates, value objects, domain services and application services, and also domain events to create notifications for the other services that run on different bounded contexts. Kafka. For the patterns like Saga and CQRS, when you follow event-driven approach, you will need to use a message bus to use in event notification. I will use Kafka for this purpose, which is resilient as it holds the data in persistent disk store, and it is scalable thanks to the internal partitioning strategy. I will mention more about Kafka in the coming sections, but to summarize, Kafka is the concept of topics to store the data, and it provides producers to publish the data on Kafka topics and consumers to read the data from the Kafka topics. I will use Kafka in the implementation of Saga, Outbox, and CQRS patterns. Saga, invented in a publication on 1987. Saga is used for long-lived transactions. You will learn how to apply Saga pattern to accomplish a distributed transaction across multiple services. The idea behind Saga is to create a chain of local ACID transactions to finalize a long-running transaction across services. For example, as you will see in the next lecture, in this course, you will have a food ordering application that has order service, payment service, and restaurant service. To complete a food order, the application will need a successful payment as well as a restaurant approval. For this scenario, I will implement the Saga pattern using Kafka as the event bus and let the services communicate using events with choreography approach. There is also orchestration approach to implement Saga pattern that uses an orchestrator to drive the Saga. I will use choreography using events. However, I will still use the order service to coordinate the Saga pattern, as you will see in the implementation section. You will see that in the choreography Saga solution, there is no need to use a framework such as Eventuate or Axon. So I will show using a choreography-based Saga based on events using Kafka without additional framework. Outbox. As mentioned in the Saga pattern, when you have multiple services involved in a long-running transaction, how will you accomplish consistency? Think like this: you have two services, so you have two local transactions to accomplish a Saga. First service does some local ACID transaction and publishes an event to notify the second service. Second service listens the event and does its local ACID transaction and publishes another event. Then first service listens the event from the second service and completes the Saga. What is the problem in this scenario? You see there are two local ACID transactions, but what about the event publishing? How to make sure the local transaction plus publishing the event operation works in a consistent manner? If you just first commit the database transaction and then publish the event, if the publish operation fails, Saga cannot continue, and you will leave the system in inconsistent state. Instead of that, if you first publish the event and then try to commit the database operation, things can even go worse. The local database transaction can fail. In that case, you would have already published a wrong event, which you should never have published. To solve this problem, there are two approaches. First one is using direct event sourcing, which means don't use a local database and directly publish an event, which will be listened by the second service to continue Saga operation. However, in most of the cases, you will need to use a local ACID transaction, especially if you deal with monetary operations. In that case, you can make use of Outbox pattern. In this pattern, you don't publish the events directly. Instead, you keep your events in a local database table called Outbox table. Note that this table belongs to the same database that you use for local database operations. In that case, you can use a single ACID transaction to complete your database operations in the service, plus the insertion into the Outbox table. So you will have a strong consistency up to this point. After this, you will complete the Outbox pattern by reading the data from the Outbox table and publishing the events. For this, there are two approaches: pulling the table data or using CDC, Change Data Capture approach, which will listen transaction logs of the Outbox table. In both cases, you should do the implementation to be sure that you don't miss the events in the Outbox table and they are safely published into the message bus. I will use pulling Outbox table approach and handle possible failure scenarios in the implementation section. CQRS, Command Query Responsibility Segregation. With CQRS, you can design, read and write parts of your system separately and allow to read your data more effectively. This is because you can use different data stores for read and write parts. For example, say you use a relational database for your write database and you send your data asynchronously to Elasticsearch. Then you can use this Elasticsearch to query your data more effectively. Besides, it will allow you to scale your read and write systems separately. As a natural result of a distributed system, again this pattern will end up with eventual consistency. Because after you put your data on write database, there will be some delay until your data ends up on the read database. Note that the same Outbox pattern should be used with CQRS pattern also, so that you can be sure your local transactions and publishing event operation runs in a consistent manner. Kubernetes and Docker. Kubernetes is a container orchestration system that automates deployment, scaling, and management of cloud-native applications. It allows to run Docker containers while reducing operational complexities. You will learn to containerize your services and first run them locally using Docker. Then you will create a local Kubernetes cluster and put your Docker containers in this local cluster. Basically, you will create deployments and services for each microservice and run them inside Kubernetes. To run Kafka in Kubernetes, you will use CP Helm charts. And for microservices, you will create Docker images locally. Google Cloud and Google Kubernetes Engine. You will deploy your application to Google Kubernetes Engine and learn how to use G-Cloud command line interface and how to push local container images into Google Container Registry. Finally, you will run and scale your services that you have developed in this course on Google Kubernetes Engine. Alright, in the next lecture, I will continue with the project overview to give you better understanding of the application that you will develop in this course. Please note that I have updated the captions for the videos, so you may also follow the course using subtitles. Also, remember to download the source code from lectures 61, 66, and 96 before starting important changes. You may use the source code as a reference or to skip some parts that you already know or learned previously in the course, because the implementations of the second and third microservices are similar to the first one. So if you would like to practice more, you may code along them as well. Otherwise, you can use them from the provided source code directly. So I will see you in the next lecture.